Greetings. My name is Charles Mullen, and today we're going to briefly talk about stoichiometry. What is stoichiometry? The word itself sounds really complex, but it's actually a fairly straightforward concept. Stoichiometry is defined as the quantitative study of reactants and products in a chemical reaction. In other words, it is the part of chemistry that studies how much of substances are involved in reactions. Before delving further into stoichiometry and what it is, I want to really quickly outline the terms I first used in the definition of stoichiometry. So, a chemical reaction is a process in which a substance or substances is changed into one or more new substances. Within a chemical reaction, there are the reactants, the starting substance in a chemical reaction, and the products, the substance formed as a result of the chemical reaction. An example of a standard chemical reaction is aluminum and oxygen forming together to form aluminum oxide. We can see in the equation that the reactants, aluminum and oxygen, combine together to form the product of aluminum oxide. We can't talk about stoichiometry without talking about the mole method. So let's quickly go over what the mole method is. No, it actually has nothing to do with that type of mole. Nor does it have anything to do with that type of mole. Right, these are the moles that we're interested in. The mole method states that stoichiometric coefficients in a chemical reaction can be interpreted as the number of moles of each substance. So let's look at this equation. Nitrogen plus hydrogen creates ammonia. But it's not just that. These coefficients show the number of moles that these represent. So really this is saying that for every 2 moles of ammonia, 1 mole of nitrogen, and 3 moles of hydrogen are required. This allows us to create mole ratios with this given equation. We can say things like 1 mole of nitrogen is stoichiometrically equivalent to 2 moles of ammonia. We can also create other things like these. 3 moles of hydrogen over 2 moles of ammonia, 1 mole of nitrogen over 3 moles of hydrogen, or any of their reciprocals. This can only work, though, if the equation is balanced. If the equation is not balanced, the mole ratio will be incorrect, and the conversion factor will be incorrect as well. Understanding the molar relationship in a chemical equation allows us to solve stoichiometric equations. Now that we understand stoichiometric equations, let's look at how to actually solve them. First, we write the balanced equation for the reaction. Once we have the balanced equation, we can convert the given amount of the reactant to the number of moles. Then, we can use the mole ratio from the balanced equation to calculate the number of moles of the product formed, based on the mole ratio of the product to the reactant. Once we have the moles of the product, we can convert these moles to grams or other units. When solving stoichiometric equations, one must have the mole ratios from the balanced equation and the molar masses of the elements from the periodic table. That's how we get to grams. Let's look at 4 common types of conversions: mole to mole, gram to gram, mole to gram, and gram to mole. With the molar ratio, we can do any one of these conversions. And we'll actually see that doing these conversions are similar to the factor labeling method we saw in previous chapters. Let's look at the first example. We have the given equation. Carbon dioxide plus potassium hydroxide creates potassium carbonate and H2O. How can we determine how many moles of potassium carbonate are produced if there are 5 moles of potassium hydroxide? The first thing we have to do is balance the equation. To balance an equation, we're simply looking for the constituents of the reactants to equal the constituents of the products. In other words, does the number of carbon equal the number of carbon on the product side? In the original equation, we see that the number of potassiums do not add up. However, if we add a 2 or 2 moles of potassium hydroxide, we find that the equation is then balanced. This is our balanced equation. And from these, we can create the molar ratios. So we set it up like we would a conversion. 5 moles of potassium hydroxide is in a ratio of times the ratio of 1 mole of potassium carbonate over 2 moles of potassium hydroxide. When we do the math, 5 divided by 2, we cross out the like terms, just like we would in the factor label method, and we're left with moles of potassium carbonate, 2.5 moles to be exact. In example 2, we use grams. It's the same method, but one more step. Determine how many grams of carbon dioxide are required if 3.8 grams of H2O are produced. Once again, we set up our equation. 3.8 grams of H2O. Using the periodic table, we know that 1 mole of H2O is equal to 18.015 grams. We know this simply because we add the molar mass of 2 hydrogen atoms and the molar mass of 1 oxygen atom. Again, all are found on the periodic table. Going down the line, we then create another ratio, 1 mole of carbon dioxide over 1 mole of H2O. In the balanced equation, we see that for every 1 mole of carbon dioxide, 1 mole of H2O is created. And to further convert to grams, we once again find the molar mass by looking at the periodic table of carbon dioxide over 1 mole of carbon dioxide. And as we go down the line, we see that everything is crossed out and we are left with grams of carbon dioxide, 9.28 grams. For moles to grams, again, the same method. We create the molar ratio, 1 mole of potassium carbonate over 1 mole of carbon dioxide, and 1 mole of potassium carbonate is equivalent to 138.204 grams of potassium carbonate. When we cross everything out, we are once again left with grams of potassium carbonate, 415 grams. For our final example, we start with 10 grams of potassium carbonate, which we found the grams, we know the gram molar mass previously, 138.204 grams. We set that up with the molar ratio of 2 moles of potassium hydroxide for every 1 mole of potassium carbonate produced. And when we do out the math, we know that 0.145 moles of potassium hydroxide are required to create 10 grams of potassium carbonate. And so, that's stoichiometry in a nutshell. Literally. I hope you enjoyed it.